Do you have group? No, no. Do you have some class group?
Yeah.
Just message them that come to at least online, because today is only simulation, so they should know this is very important simulation. I have only one student online. Tell them to join. Please post on the group. So Farhan, you want to do all the experiments? Yes. Now you have lectures. Also, you can log in with your NCST ID. Please post on the group that they all of them should. Yes. Only one student. Yes, only one student online.
Tell me, come.
2. Because all of them, I will put them absent. No, you do you have your own username and password? You don't have? Why? You have your email.
Yes, I have my email.
You can use that. You can just use your ID. You just write your ID and then your password. That's it.
Okay, I got it already.
Doesn't what does it say? Maybe it says that change your password.
Change passport.
Yes.
Type your
Which is up to. This is the home.
What is it? Yeah, new and then remember other favorite.
Did you put that in computer?
Yes, that's why they are joining.
They're saying
The link is there. Hello. It's okay. So link is on the Moodle because one student already joined. Tell them go to the week number. Tell them to go week number. Yeah, this is the link. Thursday. This is the link. Here, if they go to this week, week 28 November to 4 December, this one, and then this is the link. Three students. Yes. One is me and two more. Tell them to join. Working? Okay.
Hello, Miss. Good evening.
Good evening.
I just saw the link.
Students are not joining on. They don't want
I
to
just-
study?
No, Miss. I just saw the link. It was not there.
Okay. No, link was there. You couldn't find it. Link is there. I didn't post a new link. Link is here. This one. I posted
Sorry,
it
Miss.
last like on Sunday. I posted all the links.
Sorry, Miss. I didn't see. Miss, I'm on my way to the college. Is it okay if I will be late or not?
When you will come?
I am in the road actually.
Okay, so then pay attention to the lecture because this lecture is very important.
Okay. I'll be online until I reach there.
Yes, okay.
Thank you.
No problem. Okay. You cannot see my screen, I think. Everyone is here? Hmm,
Yes, I can.
okay.
So. Yeah, it doesn't need the so try. Do you have time? Try something first capital, then something static, some 1, 2, 3, something, then one not count. Mix things, then small mix. Understand this? You will help me to remember.
Please everyone pay attention. Okay. So today we are going to start lab number 6, experiment number 6, which is natural response of RC circuit. So can anyone just from the name, what do you understand? What is natural response? Natural response. Something which is natural without any force. Okay. So if you don't have any power source in your circuit, as you don't have any power source here, do you have? Then these elements, capacitor and inductor, you know, these are the elements which store energy and also they can deliver energy. So, and then resistor, it only absorbs power. It only absorbs energy. It doesn't deliver, it doesn't store, it just absorbs. But they, capacitor and inductor, they store energy and then they can deliver that energy. So whenever there is not any power source in the circuit, then these elements will show their natural response. Okay, this definition is also written here. The natural response of a circuit is the response of circuit which contains an energy stored elements. It has energy stored elements such as capacitor and inductor without any power source. So normally we were having this kind of circuits before. This is the power source. Voltage source is also known as power source. And then capacitor was absorbing all the power. Then when we have, for example, we have a capacitor here. If we have a capacitor here, then what will happen? If this is 12 volt here, then it will start to charge from zero, and then one time will reach when it will be charged with 12 volt. Okay, and then at this time I don't need this power source anymore. Then this capacitor will deliver power to the resistor. Then it will release all the energy, it will go to zero again. And then it needs another source to charge it. Then this process will continue. So let me remove it. No, it's touching with my. Did you understand? Did you understand what is natural response?
Yes.
Okay. So this explains that this circuit has two energy storage elements. Which are the energy storage elements? And inductor. And then they will show the natural response because there is no active device such as power source here. They will show their natural response. Okay, now you understand what is natural response?
Yes.
Okay. Now the natural response of a resistor capacitor circuit is decaying exponential. Why? Because if you consider this is a capacitor graph, so voltage we see this is time, voltage across capacitor. This will start from zero, and then when it will reach its maximum value, which is the maximum voltage value, then it will remain constant. Then when if there is a resistor connected, then it will release all its energy and then it will go down. Again, it will charge. So this cycle will keep on going. You have this waveform in your. Did you see the response of the capacitor? So it will start from 0 and then gradually it will increase with time. Okay. So this voltage across capacitor is given by V0 e raised to power minus t by RC by exponential because it shows the exponential behavior. Okay. Then this RC is equals to tau. What is tau? This is the time constant. Yes, this is the time constant. It's written here. What does time constant mean? The time which it takes to charge. How much time the capacitor takes to charge and how much time it takes to discharge. That is represented by tau. Okay. So today we will calculate this tau using this equation also by simulation. Okay. So this will be my tau charging time. So one more thing, if the capacitor value is smaller, capacitor value, for example, value of is small, then my tau, my time constant will be small. That's why the large capacitor takes more time to charge because their capacitance value is large. Okay. Whenever the capacitor value is small, the time constant is also small. Okay. So do you understand this equation? Now here, as I know that tau is equal to R into C, I put RC in this equation and then my equation becomes V not e raised to the power minus t by tau. V naught is my input voltage. Okay, this is my input voltage. Just remember this equation. Now, when the capacitor is charging, then my equation is Vs into 1 minus e raised to the power t by RC. So in today's experiment, okay, I will explain it later. Here, if you see, this is my charging time, and here, when my t time is equal to 1, at that time, my capacitor is 0.63% charged. When my time, this is time. So at time equals to 1, this is 1. This is 0. My capacitor is 0.632% charged. This is constant. This will remain the same. And when during the discharging, at time equals to 1, my discharge, the capacitor is 36% discharged. Okay, these two values are very important. I will tell you how I got these two numbers. So when, just remember, whenever the capacitor is charging, my equation is this, Vs into 1 minus e raised to power minus t by Rc, and it is discharging, then equation is Vs e raised to power minus t by Rc, and for capacitive circuits, capacitive, tau is equal to R into C, and then for inductor, my tau is equal to L by R. Okay, these two relation also remember. So clear? Clear? Any questions? Questions? Did you understand it now? What we were doing in the pre-lab? Okay. So now, what happens about? So as I told you, when the capacitor is charging, my equation is this. So if I put t is equal to 1 RC in this equation, what will happen? My equation will become Vs is equal to, sorry, Vc is equal to Vs into 1 minus e raised to power minus 1. Yes. When I will put this in calculator, I will get 0.63. So this 632 is taken from here when t is equal to 1. Then I multiply it with my voltage, which is equal to 12 volt. I will get this. Then in the simulation, what I will do is I will take my cursor value at this point at t is equals to 1, and then I will calculate my tau with the simulation. Okay, this is the procedure. Then at t is equals to 2, my capacitor is 86% charged using this equation. Then it will be e raised to power minus 2. Then I will get 0.86. Then it means 86% charge. And then my VC will be somewhere here. Then here I will get my value 0.86. Clear? Is it clear? Yes. So this is the procedure. Then at t is equal to 3, 95% charge. Then at t is equal to 5, let's suppose here my capacitor is 100% charged. Okay. So then at this time my voltage is 11.92. It's almost equals to 12 volts, which I gave as input. Okay. So then it's clear, or any questions? This is the theoretical background behind it. Okay, why you are getting these waveforms. Next. So this is discharging. For the discharging, the equation is this. Here again you will put T is equal to 1 into RC, 1 RC. Then 36.8% discharge. Please, you will do it in the lab. So this concept is very important. Then you will put 1 here. You will get Vs e raised to the power minus 1. Okay. So this e raised to minus 1 will give you 0.36. Okay. You will multiply it with 12. You will get this value. It means at 4.42 volts, my capacitor is 0.36% discharge. Then I will put T is equal to 2. RC it will be equal to 2. This value 0.135 multiplied by 12 will give me this number. Similarly, 3, 4, 5. My capacitor at 5, T is equal to 5. For example, here my capacitor is 0.7% charged. And then it means almost equals to 0. Okay. So this is the procedure for charging and discharging. This is the mathematics behind it. Okay. Okay, so we did it. Okay, now how we will do it? Actually, this is the function generator. What we are doing is, I forgot to tell you. Before we were using this DC voltage, but today's lab is related to the AC voltage. AC voltage. Symbol is this. You will give AC input, not a DC. Okay. So, for example, this is my function generator. This device generates different waveforms, sinusoidal, square, triangular, this kind of waveforms with different ranges of frequency, 0.01 up to 100 kilohertz frequency. So this device we will use today, and we have it in our board also. So this function generator, the purpose of this is to generate different kind of waves at different frequencies. Okay. So this is not 10. Okay. Then we will use oscilloscope. What is oscilloscope? Are you familiar? No? So with the oscilloscope, we will see our input and output signals. So for example, hello. Did you attend all the lecture? Did you attend all the lecture?
Yes.
So this is my function generator. It gives, for example, if I give square waveform from my function generator, and then here's the capacitor, if I connect my probe of my oscilloscope here, then it will give me input voltage waveform. If I connect it here and then with ground, this second terminal is connected with the ground. Second will be connected to the ground. And then this also with the ground. So this will give me the voltage across the capacitor waveform on the oscilloscope. So this device I will view my signals on this device and then I will give the pulses using this device. Okay, input signal using function generator and then I will view my waveforms using oscilloscope. Okay, so using the oscilloscope I can see if there is any fault in my circuit. I can see using oscilloscope. Okay, that's it. So what we do is we connect oscilloscope like this. It has channels, channel 1, channel 2. So with channel 1 I can see input waveform, with channel 2 I can see output waveform. Okay, here 2 channels. Oscilloscope has 2 channels. With one channel I can see input waveform, with the second channel I can see output waveform. Okay, then this is your pre-lab. This is your lab experiment. We have 1 kilo ohm resistor, we have 0.2 microfarad capacitor, and this is my function generator. I will generate square waveform. I will adjust frequency here, and then I will get the input waveform by connecting with channel 1 of oscilloscope. This is my oscilloscope in multisim. Then with channel 2, I will see my capacitive waveform. Now, can you tell me which waveform is this one? Which waveform is this one? This red one. This red. There are 2 waveforms. Which waveform is this one? See from here. Which waveform? Which signal is this? This square one. What? Channel 1, but which signal? This is my circuit. Which signal is this square waveform? With the function generator, what I give? Square waveform. My input is square waveform. Using this, I give square waveform. Then this is my input waveform, which is 8. Then what is this waveform? Output of which element? This capacitor. I showed you before that when capacitor is charging, the waveform is like this. Here. When capacitor starts to charge from 0, the waveform is like this. So I got the same waveform here. This is capacitor waveform on channel 2. Okay, then what I will do is I will change my cursor to which value? You remember the equation? V input, Vc is equal to V input into 1 minus e raised to power minus t by tau. This value is 0.63. I explained you how. And then V input is 8. So if you multiply 8 with 0.63, you have calculator. This will give me 5.04. Okay. One cursor is at 8 volt. The other cursor I will change it to 5.04. Then I will see my this time, which is here. This one. 101.105 microsecond. What is this time in millisecond? How can I convert it in milli? This is my tau. So tau is equal to 0.10 millisecond. Okay? And then how we will calculate it theoretically? Tau is equal to R equivalent into C equivalent, RRC. So R is equal to 1K, 1000 multiplied by 0.2. Sorry, this is 0.2. So for this, I think the Okay, so then this value is, just calculate this, I think, because I calculated this for it. Anyway, then 0.2 into 10 raised to the power minus 6. This will give you almost some value around 0.1 millisecond. So then I will put these two values in my tables. Which one? The input? 8 volt. 8 volt. Yes. How much? 4.9. Okay. Because I didn't. 4.96. And then calculate this also. How much? This is 0.2. This is 0.2, I think. Then I will move my cursor to 4.96, not 5. 4.96. Then I will check this number. And then this number should be exactly the same as I will check this number here. I will see it here. Okay? This we will be doing it today. Then the procedure is this. Then next is using the inductor. You know how I can remove these waveforms. Okay, now with the inductor. 1 millihenry inductor, 1 kilo ohm resistor. Okay, so same procedure I will give. The procedure is written on the lab sheet. You will choose your function generator. You will give frequency. You will set here frequency, input voltage, peak voltage. You will set here. This also I will explain you what is peak voltage. So then 1 ohm resistor and then 1 millihenry inductor, and then how you will calculate tau theoretically. L divided by R. So this will be 1 minus 3 divided by 1000. This will give you 1 microsecond. L is here. It's given 1 millihenry. It's in the lab sheet. So this is 1 microsecond. Then with the calculation, you will check it with this equation. VL is equals to V input e raised to the power minus t by tau. Okay. Then this will be, then you will change your cursor. For example, if this is, how much this gives you? E raised to the power minus 1. Someone can do. Or okay, I will do it. I think this is 0.63. It's here 36.0.36. Okay, then everything is removed now. Okay, then first is theoretical calculation. This is L by R. Tau is L by R. I got it. How much? 1 microsecond. Then how you will calculate it theoretically? VL is equals to V input into e raised to the power minus t by tau. Okay. Then this will give you 0.36. Okay. Multiply by input. So how much is this? I think it was 5 volt. I don't remember. Okay. So then you will move your cursor to this, whatever result you will get. For example, I got 3.6. I think it was 10. So that's why it's 3.6. Then you will move your cursor to 3.6 here. You will see the number here. Input was 10 volt. So I wrote 10 volt here. Then is your tau, which is equal to 1.07. It's written here. From simulation, tau is equal to 1.037 microsecond. Clear? Easy? Yes. So clear? I will help you, no problem. So today, no pre-lab, it's fine if you didn't do it because these things were new to you. So follow the procedure. These two equations are important, and this also this, and then today we will only simulate with inductor and capacitor. Capacitor 2 experiments, pre-lab and the lab experiment, and with inductor only 1. See these waveforms. You should get these waveforms, and then I will help you. Okay, start your experiment. One more thing, sorry. One more thing. Let me remove this. Okay, one more thing here, Abdul Aziz. There is peak voltage, then there is peak to peak voltage, and then there is RMS voltage. These things are important for sinusoidal voltage. For example, if you have sinusoidal input signal, okay, then what is this voltage? Any guess? Yeah, maximum means V peak voltage. And then which voltage is this one? Negative. Negative VP. So can anyone tell me peak to peak voltage? How much is peak to peak voltage? For example, if this is 5 volt, VP plus VP. Yes. So this will be equal to 10 volt. Peak to peak is upper peak plus negative peak. Peak to peak is 10. So in this case, V peak is equal to 5 volt. V peak to peak is equal to 10 volt. And then RMS is equal to V peak divided by square root of. RMS is the effective value of this sinusoidal waveform. Root means square. Okay. So in your function generator, you will always put peak value, but your output will be the peak to peak value. Here you can see it. My input here I will give 5 volt, but you see here my peak to peak is 10 volt. Okay. Input will be peak voltage, output will be peak to peak voltage. Just check this. Okay, let's start. Okay. I erase this. Make open multisim in your put some. Okay,
Open multi-sim. So, ability, how you learn? Okay, then do it today. Do it today and by seeing that. Okay, just do it. Start from here. Yes, do it from here so that you learn. I will give this expanding. I don't know how you will do it. You don't know? Yes. Please turn off. Open multi-sim. Open multi-sim. Okay. Build this circuit. Open multi-sim. Ready? Yes. Yes, but how you build it? Right, but how? Okay, explain. Go there because all the experience there I you know all the you know all yes, and then just forget about this. Start from here. Start from here. Okay, you know how to take function generator? You know? Okay, but do you know how to take function generator and oscilloscope? Yes? Yes? Okay, I will explain you. So, for example, this on so here on this side, this is function generator. If you just take your mouse there, it will show you. This is coming here, writing. This is function generator. Just click it and drag it here. Okay? Yes? So, and then oscilloscope is this one. This is oscilloscope. Just see. Oscilloscope. Take it and drag it here. Okay? And rest of the things you know how to take. What happened? Come to this. Come. Because today you will work with computer. Please come to that. Adi will do alone. Everyone will do alone. Yes. Okay. You will do yourself. Because this experiment is very important. You have to do alone. They will do alone. It's okay. Good. And then did you get your graph? Okay, I will confuse the graph. If when you build your circuit, when you call me, I will come to you for the simulation because Don't do the simulation without me. Otherwise, the results will be wrong. Yes. So not this one. I told you. Why don't you see there? And I'm see here. This is written. Click it. Bring it. Then function generator go back. Second one. Now build yourself. Build yourself. Same. Instead of this, put capacitor first. With the capacitor, it's easy. In the exam, you will be like this. Today I am helping, but in exam I will just stay silent. Okay? Consider you are sitting in exam. Okay? No. Board also, you have one board. One board also. Okay? Ask me. Yes. So you know how to take this. Okay, I will give a demonstration. Okay, if you don't know. Okay. So see here. Why you are laughing, Isa? So okay, see here. This second number. This is function generator. Take it and put it here. Then the fourth number is oscilloscope. Take it and put it here. Rest of the things you know how to take. This is resistor. Just go here. Take from go down. This is resistor. Put the value 1K. Put it here. It's easy. Then go to capacitor. 1 microfarad. How much? Put it here. Okay, so it's easy. Take a ground from sources. For this experiment, we are using here, so that it's exactly this getting away from exactly here 8 volts or whatever it is. How much is it? This one. This is not correct. This is not correct. Whoever has this, they use marks. No, okay, so resistor. So this. Now, see. No. So VP is equal to 4. So it means peak to peak is equal to yes. Okay. Understand? Okay, then close this. And then from here. The benefit, you will use it always in your life. Because whenever there is sinusoidal signal, you if whenever there is anyone can ask you, and the peak is this one, but peak to peak is complete. This is part your time. Okay, so this is yes, this is the other. Yes, yes. We are doing 3.2 micro. Stop it. If you want to change the color, for example, then you change this color. Okay, then. Choose something.
Yes.
Yes.
You want the 4 channels to this podcast.
Stop. And now the cursor is now the mathematics. So I will show you there. This is yours. So okay, the one is now we will take them to the and we this will give you 0.1 million. So you know this is a student of my this is 10 equals 3 will cancel this on 1.3. So down to 0.1 million. Okay. Here how do we calculate this? The equation is P is yeah, this because I think that